So in this video, we'll be talking about the divergence of a vector field. Let's talk about the definition first. If fluid at a certain level in a pond or river, it flows according to a vector field, we'll call that vector field big Fxy. The question we want to entertain is, what derivatives would represent the flow of water through a particular point? Now we're going to break that down into components. What derivatives would represent the flow of water through a particular point in the x direction? Well, if you're considering only the x direction, a multivariable calculus student will recognize that as a partial derivative because y is being held constant. So we go to the x component, which is next to the I, and that's little f. So we're talking about the partial derivative of f with respect to x to give us a representation of the flow of water through a particular point in the x direction. But what about in the y direction? Well, again, that implies holding x constant, so we're talking about a partial derivative of the y component, which we call little g, with respect to y. Now, what do we do with these two things? They're scalars. The definition of divergence refers to adding these two things together. So if we add these two partial derivatives, that sum will give us a gauge or measure of how much the vector field is changing in a certain direction. Remember, the direction was defined by little fi plus g of j. So by taking these partial derivatives together and adding them up, we're somehow quantifying how much this flow is changing in a certain direction defined by this vector field big F. And since partial derivatives are used to form this sum, we can think of the sum as a dot product of a del operator. Perhaps you remember del when we talked about the path of steepest descent. Well, now look at it as a del operator, that is, taking partials with respect to something. And if you take that dot product of a del operator and the vector field f, you often find in textbooks the notation del dot big F. That gives us a scalar measure of the change in the vector field in a particular direction. And that is what we define divergence of f to be. So keep this key point in mind. Any flow vector into a point, it can be broken down into its x component, contributing to the side movement, and its y component, contributing to the vertical movement. So now that we got the definition of the divergence of a vector field, let's see if we can have some more conceptual understanding about what actually is going on here. Let's take two vector fields, and here's our del operator. Here's a common way that it's written. Del is equal to partial with respect to xi plus partial with respect to yj. It's going to operate on an actual vector that has components defined. We call that vector field f. So del dot f, again, is a common notation. And let's interpret these results. Well, the computation is very easy to do. If you're having big F of xy equals xi plus yj, well, that's easy stuff. Partial x with respect to x, that's 1. Partial y with respect to y, that's 1. And 1 plus 1, well, I think everyone can handle that, is 2. And with this particular vector field f, a different one, let's see here, they have y times i. Let's say yi minus xj. It's a little bit different because now the partial derivative of y with respect to x is 0. Partial derivative of x with respect to y is 0 because we're differentiating partially, so we get a divergence of 0. But what does this mean? Commonly, some vector fields are shown superimposed with these problems to help us appreciate what it means. Here we find vectors headed away from the origin in the first problem, where the vector field was simply xy, that is xi plus yj. And here we have what you could call a clockwise flow in the stream or the pond. And we want to understand, well, why is this vector field, the first one, why does it have a divergence of 2? How is that related to these vectors headed away from the origin, if you will? And why is it that this circular vector field in the B question has a divergence of 0, perhaps somehow communicating to us that things balance out in some way? Well, let's see if we can use our calculus skills from single variable calc to help us find out what the pathways are. That is, what are the actual curves that these vectors are following along? If we can solve for those curves, those solution curves, if you will, then perhaps we'll get a better handle on what divergence actually means. So first, we note that if big fxy, which is again that function I gave you earlier, little f comma little g as a vector, if that's a velocity field, think of it as the velocity of the water molecules or the water particles in the stream or the pond we're talking about. And let's now refer to the vector xy expressed in some terms of a parameter t. Let's think of that as a position function in vector form. Then we see a direct correlation. We know that x prime of t would equal the x component of velocity, if you will, and y prime of t would be that y component of the velocity field. So by our knowledge of the chain rule, dy dx is simply that dy dt over dx dt. But wait a minute. dy dt was g of xy. That was the y component of the velocity field. So we put that up top. And dx dt is x prime of t. That is little f of xy of the velocity field, little f. So we put that on the bottom. And we recognize this, hopefully, as a first-order differential equation that can be solved by the method of separation of variables. BC calculus flashback. Let's see how that looks. So you have dy dx equals, now remember, in the A question I gave you in the previous slide, the g of xy was y. That was the y component of the velocity field. That was y. And the x component, little f, or the I component I should say, there is little f of xy. That was x. So again, just going through the motions here, something I'm sure you're familiar with. Separating of variables, you have dy over y equals dx over x. You take the integral both sides, you get natural logarithm of the absolute values on both sides plus an arbitrary constant. You exponentiate both sides, you get to this stage. Now we know when you have absolute value on both sides, you have different possibilities. Either they're both positive, both negative, you drop the absolute values, or one of them's positive, the other one's negative, and you put a negative in there to balance it out. In either case, all of those possibilities can be absorbed by this e to the constant 1 plus or minus that, and you can just call that another constant. So the point for us is that this indicates that the flow curves, that is, the curves along which these vectors in the vector field illustrations are following, they're lines that go through the origin. We recognize y equals a constant times x as a family of lines that go through the origin. So since big F of xy is a velocity field, we can represent the speed of a particle at a point. We know that speed is the magnitude of the velocity, or the norm of velocity. So if the velocity was, what was that, xy, then the speed, right, would be the square root of x squared plus y squared, taking the norm of the original vector valued function I gave, which was x comma y. That's part A that we were doing from the previous slide. But notice how this changes a bit in its appearance. I hope you'll recognize what's going on. If we, using the formula for the flow curve, right, we can express this as, let's think now, we already know that y equals cx. We put that here. We have the speed being the square root of x squared plus c squared x squared, which is simply the absolute value of x times the square root of 1 plus c squared. So what does this tell us about the speed as we go through this vector field, or this velocity field? Well, that really tells us that the speed of this particle in this vector field would increase as the magnitude of x increases. I don't care if x gets very big, very positive, or very negative, the magnitude is going to increase, and we're saying basically that that speed will increase as the magnitude of x increases, because this square root of 1 plus c squared is held constant. So look at this vector field that I showed you with part A earlier. Here earlier we noticed that the vectors were pointing away from the origin. I don't care which way you looked at it, right? Now, what does it mean with regard to the magnitude of these vectors, right? If you look at this particular box that's superimposed on this vector field, we note that the arrows coming into the box are a bit shorter than the arrows that are exiting the box. This means that the net flow out of the box is positive. That is, more fluid is exiting at any particular point, or any region of a particular point, like a box. There's more fluid exiting that box than there is entering that box. But this harmonizes with what we saw earlier with regard to the speed of the particle. We knew that as x got bigger, as you moved further along, right, we knew that we would have a bigger magnitude for the speed. because you have the absolute value of x times this constant. So we were expecting that, and we saw it from our solving of the differential equations. So in this case, we say that the divergence is positive, and that harmonizes with what we did earlier with del dot f. We got a positive 2. All it means is that we expect more to be flowing out of a particular point, more water to be exiting a particular point than what's coming into that particular point. So we kind of saw it two ways. We saw it by solving for the family of curves, seeing that as x gets bigger, things flow away a lot more, and we saw it with our scalar calculation called del dot f. We got a positive 2. So think of positive results of divergence referring to moving away. Of course, negative results would of course mean the opposite, headed towards a particular point instead of away. Let's now look at the second example I gave. Part B of that previous slide had the vector function yi minus xj. Setting up the same situation, we get a different type of solution curve though, because now we have negative, let's see, x over y, okay? And that would be dy dx equals negative x over y, separating of variables. And this one, we don't have to deal with ln this time, just a nice little power rule. But when you balance everything out and make the appropriate substitutions with constants, you get a familiar face, so to speak. You have x squared plus y squared equals c. We look at that as a family of circular pathways. But we could also, again, do the little trick we had earlier. If we took the speed of a particle at a particular point, which is the norm of this velocity vector function, we would get the square root of y squared plus x squared. Well, that just looks like the square root of the family of curves. Let's see what we can do with that. This really indicates that the flow curves for this vector field are circles, right, centered at the origin. And since fxy is a velocity field, we can represent the speed of that particle the same way we did before. And using the formula for any flow curve, we see that speed really, this is speed, is a constant. Speed doesn't change. Speed is this constant called the square root of c. And since the speed of any particle on a given circle centered at the origin is constant, we can then conclude that the flow into the box superimposed on that vector field should be equal to the flow out of any box in that vector field. So the net flow is 0. And of course, in this case, we would say that the divergence of this vector field is equal to 0. Again, because the speed turned out to be constant, it didn't change as we move from point to point. And that harmonizes with the del dot f calculation we had earlier. So hopefully that gives you a better handle as to what that 0 actually means. Let's summarize. In the first vector field, right, the del operator was positive 2, so we had bigger vectors coming out of a particular point than were going into a particular region. And with the B part, we had this circular field, and we noticed that the vectors, they all have the same length as they go through a particular region as they are coming out. Things balance out. So remember, the divergence of a vector field at any particular point corresponds to the net flow of fluid out of a small box centered at that point. And if del dot f is positive, more fluid's exiting than is entering, and that's said to be a source. If del dot f is negative, then more fluid enters the box than exits. That's called a sink. And those are perhaps some terms you're familiar with from your science classes, and you can actually think of a literal sink as water pours down the drain, so to speak. And if del dot f is 0 on some region, there's some terminology you need to know that, and that is source-free. We say that f is source-free or incompressible. So I'm hoping this little discussion gave you a better idea as to what divergence actually means. It's an easy calculation to get a scalar output, but what's the significance? And please keep in mind, as this slide implies, this approach works in 2-space and 3-space.